this non-planar graph you saw has the property that if I delete any single propagator, it will be planar.
Yeah.
But it's hard to imagine any other graph having that property.
Okay.
But you give me a graph, it's got to be a non-planar graph such that if I delete any propagator,
Yeah.
or maybe any two propagators, then it's got to be planar. You can think of that if you can construct one, but I think it's probably only that one. Okay, so where was I? So, that's the precise statement: is that each component correlator should correspond to a planar graph. The algorithm, therefore, is I just write down everything with arbitrary coefficients, and then project onto the non-planar sector. So mathematically, you can do that. I can tell if the graph's planar or not, and then you just kill it if it's planar. And then, once you've got the non-planar sector, then assert that that has to be 0, and then that gives you some linear equations on your coefficients, and that's the planarity algorithm that we're using, basically.
Mathematica has a function that tests if the graph is planar?
Oh yeah, isomorphic graph Q.
Oh, okay.
True or false is the answer.
Great.
It used to be you had to use a package, but now it's in Mathematics. Okay, so the second thing, and this is recently found, is this light-light OPE constraint. And before I look at that, I'm going to look at a precursor to the light-light OPE constraint, which is what we were using before we found this new thing, which it comes from the correlator Wilson-Amplitude duality. So the relation between correlators and amplitudes says that, or more accurately, Wilson loops and then amplitudes, says that in a polygonal light-light limit, then this combination of correlation functions gives you the amplitude squared. And we've considered this in the 2222 case, but we could also consider it here. And in fact, it's more convenient to rephrase it, because if this is true for different k's, then it's therefore this is equal to m4 squared, and that's equal to m4 squared. Therefore, they're equal to each other. So it's easier to rephrase it purely in terms of correlation function. So the arbitrary charge correlation function is equal to the 2222 correlation function, which is the one that we know very well. So that's what we were doing originally, and this helps us to find lots of coefficients, but not all of them.
So is this something you can prove? Has to fall?
Well, I would argue, you can look at this paper and decide whether it's proved or not. The relation with Wilson loops and correlation functions is essentially proved.
And why is it that it doesn't depend on the K charge?
Well, you sort of have the rough intuitive idea is that in the light-light limit, that's why I said at some point that you have to, it only works if I can consider correlators which have tree-level diagrams which only lie in the light-light limit that you're considering. So it has to have a tree-level diagram that looks like this. So this here it's charge 1, 2, 3, 4, 5, 1, 2, 3, 4, whatever. That guy works. Some of them don't. Some of them you can't write down this diagram. But anyway, the intuitive idea is that in this limit, the loop level guy looks like the tree level guy, but these propagators are dressed with a sort of Wilson line factor. So I get the tree level diagram multiplied by the Wilson loop going around the square. That's the that's the idea of that paper. Okay, so here we just have a relation between a known correlation function and some unknown correlation functions, and we use that to fix a lot of coefficients. Oh, there's the diagram. That's just to define what I mean by the denominator here, because I basically mean the diagrams that live in the square. However, we realise now that I can prove this version of the statement in a much more straightforward way from an OPE. And it comes from a simpler statement. So the simpler statement, put in its most simple way, is that these building blocks that I defined, if I have a building block, it depends on 6 coefficients, the BIJs. If I compare that with another building block, so this will come from a correlator with where 2 of the charges are 1 left. It will be K1 minus 1 and K2 minus 1. So I replace B12 with B12 minus 1. Then in the limit x1 squared, x12 squared goes to 0, they're equal to each other. The x12 squared is just to make the limit finite. So this is a new, if you like, correlated duality, but it's really just comes from the light cone OPE. And it comes from a slightly non-trivial, it comes from a free theory light cone OPE. And it comes from a slightly non-trivial fact that in the light OPE for a leading twist spin S operator factorizes. So here I have an OPE between 2 half-BPS guys, K1 and K2. On the right-hand side I have an operator of twist L, spin S. Then the twist actually doesn't depend on the twist at all. This is for the leading twist in each SU4 channel, whereas the spin dependence factorizes from K1 and K2. So what this means is, if I imagine inserting this into my operator and taking the limit x12 squared goes to 0, and dividing by doing the same thing for charges of 1 less, I get CK1 K2 over CK1 minus 1 K2 minus 1, and then the CS's just divide out. So the whole higher spin structure divides out from the 2 correlation functions. Okay, and furthermore, well, the precise relation between these guys is this. Actually, I didn't mention this prefactor previously, but if you go back to my ansatz, wherever it was, no, here. My ansatz here, I pulled out a factor. Of course, I didn't have to because I've got an arbitrary function here, but it was useful to pull out this factor. K1, K2, K3, K4. And now with that factor is precisely related to this factor. I've got K1, K2 divided by K1 minus 1, K2 minus 1. So with that factor pulled out, this relation gives me this very, very straightforward limit between my building block functions. So I can then go ahead and see what that means for my building block functions. I know F2, the 0, 0, 0, 0 case. Then I can look at the case where B12 is 1 and compare it with that, and so on and so forth in the limit. But also, as I go up in charge, planarity has more and more restrictions. So you've got this sort of, at the bottom end I know the full answer. With many high charges, planarity actually kills it completely. And then in between, you can in fact use this to almost determine the full answer. Oh, and this as I mentioned, this implies the previous polygonal duality. If I just do the limit in various different points in a polygon. Okay, so as I said, this almost gives us the full answer. It turns out this, so it does give the full answer at 2 loops. At 3 loops, you end up with 2 unfixed constants. And then we can use this so-called Euclidean OPE. I mean, historically, this is not the way we did it, actually. We did this first, but logically, I think this ought to come last now. So we've got 2 unfixed constants. Now I use the OPE for the 3rd time in a slightly different way. I use a Euclidean OPE, by which I mean I take x1 to x2 instead of x12 squared to 0, which is what I was doing before. And if I take the 3-3 guy, or the 3-2 guy, or indeed the 2-2 guy, I end up with this structure. This is the leading structure in the interaction theory. This is a so-called Kenishi operator. This is his anomalous dimension, and then you get this this power of x12 squared and this 3-point function. This guy, K6, is a generalization of Kenishi. It's just trace phi I, phi dot phi. So it's in the 6th representation of SO6. And the key point of these two OPEs is that there's only one operator with his quantum numbers. If there was more than one operator, then there would be a problem with what I'm about to say. But because there's one operator, it means that essentially the leading divergence exponentiates. There's one anomalous dimension, one operator, and therefore if I take the log of a certain combination of this of the full correlation function, it basically gives me this gamma k times the log of x12 squared. Again, if there were more than one operator, then I couldn't say that. But in these two cases, I can do that, and then I can use a similar trick to this trick that I mentioned previously. I can analyze the fact that so what does this mean here? So the log of the correlation function only looks like, in this limit, it looks like log of x12 squared. So I would expect log of x12 squared to the power L at L loops. But instead I only see log of x12 squared. Very much like the log of the amplitude with the cusp anomalous dimension of BDS formula. Sorry?
Especially when you write it as
Right. Yeah, no, K is Kenishi, not cusp. But I never understood why K was cusp, actually. Okay, so so we've got a reduced divergence, and again I can enforce this at the level of the integrand. I can examine where the divergence comes from at the integrand level, and then use that to restrict the 3,322 correlation function. In some sense, we'd already used this fact at the 2,2 level to restrict the 2,222 correlation function, or we could have done. I mean, you can determine it in many different ways. In other words, there's no new information from this guy, but this guy gives us new information about this correlation function, and that is enough to fix the remaining two constants that we needed to fix.
You know gamma K6?
So we don't need gamma K or gamma K6. We just need to know that. Yeah, we just need to know that there's a log. Yeah, we just need to know there's one operator there. I mean, presumably you could work. In fact, at the 2,222 case, we used the correlator to work out the Kenishi anomalous dimension and work with Volodya Slanov and my other collaborators. So you could do the same thing here, presumably. Well, we only know it to 3 loops so far. Well, actually, we know the integram to 4. Yeah, you could do this to 4 loops. Okay, good. So we've got all half-BPS operators of arbitrary charge to 3 loops using the above techniques. Now they're all given by the same integrals as for the 2,222 case. The only difference is, whereas I had this permutation symmetry before, which essentially meant they all have coefficient 1, now I just have some different numerical coefficients. So let me just briefly review the story. So the 1 loop you only have the box function. 2 loops you have the ladder, 2-loop ladder, and the box function squared, g squared. And then at 3 loops you have the g times h, that guy times that guy, and then you have a 3-loop ladder. You have the tennis court diagram, which doesn't appear here because the tennis court is analytically equal to the 3-loop ladder. Sorry, well, that's a 2-loop ladder, but the 3-loop ladder, which is there. And then we get to 2 new integrals. So we get the so-called easy integral, which, if you're interested, is that one, and the hard integral, which is that one. So I have these arbitrary coefficients which I need to fix for any correlation function. All the integrals are known. So the final 2 that weren't known previously, the h and e, we found a couple of years ago. Using some of the techniques that we heard about, namely leading singularities and symbology. So for those who are interested, most of them are HPLs, but there was an x minus and it can be written. We wrote it in a rather ugly way in terms of Goncharov polylogs, but you can rewrite it in a nicer way in terms of so-called generalized single-value polylogs. But the main point here is that we know the answers analytically, and therefore we know all the correlation functions analytically. So here's the result. These are the coefficients. This is for 2 loops, these building block functions, and these are the values of the 6 B's. So it only depends on whether B is 0 or non-zero. So as soon as B is non-zero, then you get the same answer for any value of B here. Again, if they're all non-zero, you get a very non-planar prefactor, and that's why this is completely dead. So the most general case is just 0. So that's the 2-loop result, and then the 3-loop result takes a couple of slides to get, I'm afraid. So there you go. These are all the 3-loop results. Again, this is the starting point. So in some sense, these are all 1. They're not 1 because they've grouped together a few graphs. But this is your normalization point, if you like. And then
why does it depend on what the non-zero value is at 3 loops, not at 2 loops?
That's a good question. So it's because the planarity is less crucial. So actually, I think it's because of the extra power, the extra numerator in the 2-loop graph. So in the 3-loop graph, sorry, the 2-loop graph has no numerator, and therefore so these B's, remember, multiply y squared over x squared. So the higher power of B, the more x 1 over x squared you get. But because I have a possible numerator term in 3 loops compared to 2 loops, then it kicks in at a slightly higher order, the restriction of non-planarity. So yeah, again, if they're all 2, we again get a 0 answer. So here you obviously somehow saw the point here, but as soon as it's bigger than 2, then we have the full answer. So if you're interested in this building block, F71508, then you rewrite 7 becomes 2, 5 becomes 2, 8 becomes 2, and then you read off. You might have to do some symmetries. I've only given the ones that are inequivalent up to permutation symmetries. So. But any building block is there. Right, I think I'm probably running out of time. Yeah. Okay. So just to finish off, let me just mention that these guys have used. Oh, I was going to make a joke about their clothing manufacturer information that they give us in this paper. Although I'd rather say trousers than pants, being British. But never mind. So they have some integrability-based way of finding all 3-point functions, which you can extract from a 4-point function using an OPE conformal block expansion, and they do this using our results. And this is the output of what they give. So this is some 3-point function squared that you get from the 4-point function, and all these numbers agree with their predictions. So. And for them, there was a non-trivial test at 3 loops because of wrapping effects and so on and so forth. There have been other tests in the 2222 case. So I'll just conclude there. Okay, it'd be interesting to do higher loops, higher points. 4-loop integrands, that's an open problem. It is to find the 4-loop integrals, sorry. We can immediately apply this technique, get 4 loops for the integrands. We've already fixed this guy, but we haven't really tried it. I mean, very hard because we're finishing this off. And then more speculatively, I'm still intrigued by sort of relation to the amplitude for these correlation functions and the twistor-based approach we did recently. Okay, thank you.
General are these generalized single-value polylogs that chance?
Well, as I understand it, I don't.
We only cover the case of 2
sure they're really functions in the sense of, I think you have to, there's some funny business with imposing the integrability constraint on at the functional level, which I didn't quite follow. Yeah, I can't really say much about that. I don't know if that's, he had some recent work, I don't even know if he's published it, his new functions, maybe you know better than.
No, that's all I'm asking.
Right. No, sorry, I'm afraid I'm. He just, I gave him the file, and he sent back this much simpler answer.
Compact form, but you're not sure what the things are to go.
No, exactly. Yeah. the fact that it was much more compact was was nice.
It's not the same as Brown's functions.
Well, the Brown ones I know about are the HPLs, single-valued HPLs. So they're just combinations of HPLs.
Yes.
And they, at the symbol level, they only have x's and x bars in subset A.
What would you?
So here I have x minus x bar as a letter.
As a symbol.
Yeah.
As a symbol letter.
Yes. Yeah.
So
Yes. Yeah, that's right. But somehow, even though he's dealing with functions, he still has some. I mean, he explained it in an email, but I haven't seen any kind of.
That's integrability conditions at the level of function C. Where we have to be careful.
You know, I think the point was it's not a Yeah, it's
It may be defined through per products.
That's the one exponent.
Yeah, for us that's the one extra letter that appears here. Yeah. At for loops, of course, we don't know yet. In fact, we suspect it gets more complicated.
Let's thank the speaker again. Okay, so the next talk will be Jake, and he'll tell us about descriptive unitarity. So he explain that. Can we turn off the speakers actually? It's buzzing in the back. Okay, I should start by thanking the organizers and for arranging this conference, and I'm actually especially appreciative of this conference in general, Amplitudes in Asia, because the results I'm going to tell you today really were only made possible by a very long plane flight back from Hong Kong last year, where Yaroslav and I were able to bother all of our neighbors and work out all two-loop amplitudes in planar n equals 4. Which will be the primary example that I'll be the punchline of the second half of this talk. What I'm going to describe today is a new prescription, a new representation of procedure to obtain, to construct loop amplitudes, I think in any quantum field theory, directly by using the principles of unitarity, just directly constructing it term by term. And the answers that will result will be that we find will be very similar to what you see, what everybody knows and loves at one loop. And in many ways, what I'm going to describe builds upon the incredible success of generalized unitarity at one loop, but avoids the complications and the linear algebra required to do integral reduction at two loops and higher, and generates just a direct, concrete, closed formula expression for the loop amplitude. I should say this builds upon work with Yaroslav Trinka and also with Simone Carnot at one loop and at two loops. And I think it was only at two loops, which we'll see in the second half of the talk, that the general prescription for how to do one loop correctly in any theory became clear. So if you doubt my confidence in this being a general procedure, wait until what we see at two loops. Okay, so we've already seen in this conference very good introductions and summary of especially generalized unitarity of one loop. A great introduction was given in Mark Spradlin's first talk, where he described the typical expansion in terms of boxes, triangles, bubbles that we have in four-dimensional quantum field theories at one loop. And in general, this continues. The idea is very straightforward. You don't know how to sum up the Feynman diagrams, and so what you do instead is you start with a complete basis of L-loop integrands, however you find them, and you fix the coefficient and you expand the right answer into this basis by fixing the coefficients according to cuts. And you can, there's a bunch of cuts. They're easy to compute in terms of trees, which is a huge advantage. The loop integrands you get to compute once and for all and put in an appendix. That's a huge advantage as well. And then you just solve this linear algebra problem to find all the coefficients. So you get, and this works in general. If you do it in d dimensions, it certainly works in general. Of course, the problem is, now, in many ways, it's extremely powerful at one loop. In fact, a little deceptively so, because at two loops, this story becomes very complicated. The linear algebra involved becomes very difficult. And in fact, I would say at two loops, it's probably heroic, and at three loops, it's impossible. So the story I'm going to tell you today, I want to really make clear, is not like generalized unitarity. It's not integral reduction. I'm not going to write down a basis and fix coefficients. I'm going to directly construct the right answer, which is a better, well, it's a more constructive approach, and it will have some really accidental, amazing benefits that was not put into this story by hand. So in the first half, I just want to review the generalized unitarity story of one loop. Again, planar n equals 4 will be the standard example throughout this talk. We'll see how to modify it in a nice way that doesn't have very much complexity, but really is going to allow us to continue two loops and higher. Okay. So one loop unitarity. So by the way, prescriptive is what I'm saying. That's the point, is that I'm going to explain a way to just write down the right answer, no linear algebra involved. Okay. So as we saw in Mark's lecture, Mark Spradlin described, the basic idea is that the endpoint, the one loop amplitude, I'm always going to use this to represent the integrand. I wish I had time to talk about integrals, but I don't, and also I don't have that much to say anyway. But the idea is that the L loop, the integrated expression, can be expanded in terms as a sum of canonical pieces. So in terms of basis integrals, which the leading term is scalar boxes, however you wanted to choose them, and then some coefficients, which we fix by field theory conditions. Plus, and in general, we have higher terms as well. And it's a remarkable fact of n equals 4 at one loop that just knowing data about the boxes, the codimension 4 residues of this topology, uniquely fixes the full answer. So we don't need to include the higher terms. But it's exactly this which even breaks in n equals 4 at two loops, which is, so this plus ... that we would normally need in a general theory of one loop is actually required even in n equals 4 at two loops. Okay, so the idea is, now, okay, over here. So what are these expressions? So I is just 4 scalar propagators. Normalized so that the codimension 4 residue found by cutting these things is unit. Why? Because it makes the coefficients obvious. Because the coefficients on this codimension 4 residue that cuts these 4 propagators in the scalar integral, we know what field theory should give, and that should be the product of 4 tree amplitudes